So now that we have the three dimensionless groups, we want to create 100 experimental data points, and we want those data points to be normally distributed, and we're going to want them to have a 10% experimental error. We're going to use linear regression and the dimensionless groups to find the relationship between the experimental data that we're going to be creating. Before we get started on that though, we're going to have to import some functions that we're going to be using throughout this. So we're going to start off by importing numpy as np. We use that almost all the time here. We're also going to be plotting, so we're going to need plotly subplots, import, make plots. Next, we're going to also want to import plotly. We're going to want that as graph objects because we're going to be making scatter plots. We're going to have that as geo, graph objects. Lastly, we're going to be having SciPy to optimize and minimize, and we'll see that later on. We'll see why we're going to need that. We will need that minimize function. It's a little slow, I apologize. Oh, and actually a mistake too. SciPy I was talking about minimize, so I typed in minimize. That's a funny one. Alright, so first we're going to need the experimental data points for this dimensionless group. We're going to have it as, for the Reynolds number, we're going to set the random uniform, and we actually already have this as given in the problem as 2,000, which we're going to write as 2e3. Then we have 35,000, which we're going to write as 35e3, and we want to have 100 data points for this. And the same goes for the Schmidt number. But for this one, the values that we have are 0.6, 2.5, and again we want 100 data points for this. I forgot a comma there, that was wrong. So with that, we want to put that into the Gillian-Sherwood correlation, which we have the equation for that as well, as 0.023 times that Reynolds number. I'm actually going to put that in parentheses because I do like parentheses. That's going to be to the power of 0.83. That is multiplied by Schmidt to the power of 0.44. Those are the exponents for this, essentially. Those are going to be the correlations for that. I believe that is all the parentheses I need, yeah. There we go. So we're going to have to create a randomized points for the Sherwood number. We're going to have it as SH. We're going to randomize it the same way, except we don't have those given, so we're going to be using a local average for this. And we're going to scale it, we're going to scale it to that experimental error, which is 10%. We can rewrite that as 0.1. We're going to multiply that by that Sherwood number again. Now we want to put the equation into a linear form so that we can perform linear regression. And we're also going to want to replace the coefficients with variables here because we're going to be doing it to our numbers, our experiment now. It's what was before was what Sherwood and all the others found. So we're actually I'm going to write a comment here just so that I can see it better. It's easier for me to understand. And that's just so that we can understand how that correlation is going to be going through. Now, actually we can keep that there. We're going to want to create a shape here. So to create the shape, we're going to type in np1s. We're going to find the ones that are like that Sherwood number. And you can see here it gives us all those values that, yeah, you can see. But we also want to add the Reynolds number and the Schmidt number, and we want to do a column stack for that. To do that, we're going to, first we're going to set that equal to x. We're going to need that as a variable. And we're going to use, again, np, and we're going to column stack np, and we're going to do the same thing as we did above there. In fact, actually, I'm going to go ahead and use that. np column stack. So we can have it like this, np.log, and we're going to have it be the log of the Reynolds, Reynolds, the log of that Schmidt. I hope I got all my parentheses right there. Good. And now we're going to find the shape of it in this sense, which we can see that as 103, and that's how many columns and rows there would be in that. But we're going to want to transpose this equation. Transpose is essentially, it's going to flip these two values over. The way to do that is actually there's a fun function, x.t.shape, and that essentially just transposes that x value, except I did it wrong. I put a capital X, I use using lowercase x's, which gives us, as you can see, the same thing but flipped over. We can go ahead and delete these though, we don't need them. We're going to now want to find the coefficients of A, B, and C for this, and we're going to be using that transpose function with it. So first we're going to set our value B as np, and we're going to use the linear algebra function. And we can see that we're transposing that at that x value. And it's going to be again at the x.t at the np, the log of that Sherwood. And this actually gives us the transpose X matrix, and by doing both sides we can obtain the vector, the parameters that we're trying to find. This is called, I believe, the Moore-Penrose inverse. So with that, we're going to find what our b value is, and see these values right here. They're actually very similar to what was initially given to us in the beginning of the problem. You can see, right here, you can see 0.829, that's close to the 0.83, 0.416, that's fairly close to that 0.44, but not this first value. The first value is a little bit off there. But the thing is, the reason why it's like that is because we found the logs. So to get rid of that, we're actually going to take e to the power of that, or the exponent of that. So we're just going to want to print, just to see how it works out, the exponent. And we're doing the b at that 0, and we're doing 0 because Python starts indexing at 0. And if we print that out, that gives us a number that is a lot closer to, in fact, that mine's luckily very close to that, the 0.023 there. Now, we're going to want to minimize the difference between the model and the experimental data here. It's a bit more, so we're going to want to define the sum square p, and that p represents the parameters we're going to find, which are the initial guesses. We're going to want to return the sum, sum Sherwood minus p at 0. Again, indexing just starts at 0. We're bringing in that equation again that we had before, but we're changing it with these p values now. Times that Reynolds to the power of p at 1 times that Schmidt, so the power of p at 2. And we want to actually take all of this together and bring that to the power of 2, and this will help us return and find the minimal values that we're looking for. It's going to make the deviation as small as possible, and we're squaring this because we want them to be possibly both positive and negative. We're squaring it to ensure that this is positive. After that, we just want to minimize again, which we're going to bring that back. Now we're using that minimize function. And we're using all those values that we had above there, the 0.23, please go away, that 0.023, the 0.83, and the 0.44. 0.44. And once we press Shift Enter, we can see, again, they're not spot on, but these are values that are considered close to those above values, which we actually have up here.